Okay, so let's kind of continue with our constraint problems here. We kind of skipped all this, not important. So a fundamental principle that makes economics an important area of study is the fact that resources are limited. Individuals need to make choices, and they're often constrained on the choices that they can make. For example, a family might want to purchase a bigger house and buy a newer SUV, but their choices are limited by their budget. A typical constraint optimization problem that we examine in this book has the following main features. An individual wants to maximize or minimize some variable y, which is a function f of x1 and x2, our multivariable function y equals f of x1 and x2. The function f is our objective function. That is the function that we want to maximize or minimize, but the individual is limited to his choices of inputs x1 and x2. This restriction on the individual's choice can be represented by yes. So that's just the function has to be greater than or equal to 0, yeah, where g is called a constraint function. It might be the case that multiple constraint functions must be satisfied at the same time, as in the case where we require the function to be greater than or equal to 0, in that the choice variables are non-negative. So x1 inputs x1 and x2 are greater than or equal to 0. Yeah, very common if we're talking about money or time or any kind of a good or something. Yeah. So you studied several optimization problem like this in your calculus class. There are different methods to try to solve these problems. For example, you probably remember writing a Lagrangian function in the class. This is kind of a etc. The Lagrangian is from Calculus 3. We'll see in the homework, all of this can be done. I think they discuss it here where the Lagrangian, yeah, we don't mean to highlight there. They talk about it here where the Lagrangian can be an important part. You really don't need to understand the Lagrangian to maximize and minimize, yeah. But they're just talking about some calculus 3 ideas. So throughout the semester, we will focus on functions f that are increasing in both x1 and x2. And we will mostly study three classes of functions. The first class of function, we had talked about this previously, we'll get into them. The first class of functions features strictly convex level curves. It's going to be the Cobb-Douglas, but we saw that previously. Yeah, strictly convex level curves, and f of x1, x2 is 0 if either x1 or x2 is 0. So one example of such function are the Cobb-Douglas functions, such as the one in figure 2.6. But we just want to kind of read about these basic ideas. We do all of this in the homework. It is kind of a Cobb-Douglas is kind of similar to, the most basic parent graph. What do we call it? This is x1 and this is x2. And remember, we found the slope lines. The Cobb-Douglas is f of x1 comma x2, a multivariable function, equals a x1 to the b, x2 to the c. We don't need all of that. But just remember, it is rather important. I'm trying to move a couple things around the page. What did we have before this? I just don't want to review too much. I have to remember when we do that. Yes, but we had the total differential, and from that we derive, uh, it is the slope. Just remember the up divided by the over equals negative. Yeah, the partial of f with respect to x1 divided by the partial of f with respect to x2. Just remember, if that's up top there, that has to be down below there. Is very easy to memorize. But if you take the partial derivatives, divide them negative, it's going to give you the slope of, it's going to give you the slope of the contour lines, yeah? So if we scroll up, I'm being very complicated here. I should just move on, but I should just scroll up to figure 2.6. When they say 2.6, they're talking about these things that resemble the y equals 1 over x, the parent graph for all what do we call that? The parent graph for all rational functions. That's what they call that thing right there. So we can erase all this, yeah. But this thing where we have that kind of y equals 1 over x look, yeah, that's one of the cases. So one example of such function are Cobb-Douglas, I can never say it, functions are the Cobb-Douglas functions, such as the one in figure 2.6. Note in the figure how the level curves are very steep when x1 goes to 0 and how they become flatter as x1 increases, and how they never touch the x-axis if y is greater than 0. So the second class of functions features linear level curves. I'm sorry, we should pay a little bit closer attention because they're talking about the specifics here. So the second class of functions features linear level curves. That was also from a previous video, but that was one where we know what the linear level curves is. So it's hard to draw the 3D thing, but the contour lines of bird's eye view, when we did the slope function, they all had the same slope of -1/2. So that's that one previous. So there's only the one that we haven't covered yet. Finally, the third class of features, it'll be down below, features L-shaped curves, which we explain momentarily. Next, we present an overview of how to solve optimization problems with each class of function. This is very important. We start with functions featuring strictly convex level curves for concreteness. So they talk about all this here about constraint functions, yes. But this is one of those things. It's 75, not 80, but we can do that. This is what a constraint is. You do have constraints basically always. Yeah. It's better that we just get to the point. This literally is straight up the point of this is the point of what is the constraint? That's what these are. This is the whole point of this section. But we have those obviously, but if we have this right here, 5x1 plus 3x2, like we did it before, this one's a little bit different, coefficients are different. But in a previous video, we set it equal to 80. That's what the constraint is. When we set it equal to a level curve, in this one here, they're setting it equal to 75. And then they have the thing greater than or equal to 0. That's the constraint. But that comes from like greater than or equal to a single level curve. Things like that are going to be some of the constraints that we're dealing with. Yeah. So we optimize, we have to find the highest point, within our constraints. It's better down below, we're going to have an example. So we go to that right now. But, if we have something like that, we're just going to find that it's always on the line there anyway. But let's just kind of go ahead and keep moving down here. Okay, so to provide some intuition, the shaded triangle in figure 2.8 displays all pairs of x1, x2, all pairs of points in the xy plane or x1, x2 plane that satisfy all constraints of those given equations there. The individual is then limited to choose. So we want to know the basic math. Yeah, we can take that constraint and make it always into a y equals mx plus b. It's the shadings that we had from like algebra 2 and all of that. I'm just trying to kind of go through this systematically because soon we're going to start a new video. But it's all kind of coming down to this. Yeah. It is always going to be that way right there. Yeah. It's going to be this one here, for the Cobb-Douglas function. It's always going to be, where the straight line hits one of the contour lines. That right there is always going to be a maximum there. So we find that out in the next video here.